Hey, what's up, Calc 2 crew, and welcome to the Daily Problem Sets. Hey, it's me, your instructor, Corey Placido. That's me, Corey. I'm Corey. Good to meet you. We're going to have some cats every once in a while, and we're just going to do some problems. We're going to have a good time with it. So let's go ahead and take a look at what we're taking a look at. So we're talking about area between curves in 6.1. And keep in mind, you should have already gone through, you should have already watched the lecture videos, right? Lily wants to make sure that you're watching the lecture videos. And then we're going to go through some extra problems. You know, if you're comfortable with the material, go ahead, attempt these on your own. And you can check your work with me. But otherwise, we're going to be taking a look at what we're working with, and we're going to get the cats to help out along the way too. They're just as invested as we are. Let's go ahead and find the area bounded between, here we have two curves, y equals x squared minus 3x and y equals 2x plus 6. Now what we want to do is we want to try to get an idea as to which is the upper curve, which is the lower curve, and where this region is bounded. So there's a lot of information that we want to sort of take into consideration here. And there's a few different ways that we could go about figuring this out. I like pictures. I'm very visual. I want to get an idea as to how this looks visually. And we got Gabby helping us out too. The cats are all over. They're all over the place. I have a lot of cats, if you hadn't figured that out yet in the video. So I'm just going to get a rough sketch going. No promises, right? But just a rough sketch. It's my x and my y axes. You can make fun of me if you want to because they don't look perfect. Then I want to think about how these curves look. Here I have your standard parabola, right? X squared minus 3x. You got the smiley face parabola opening upward. And here we have a linear function, 2x plus 6, positive slope. So I know it's going to be increasing. Now I'm not trying to actually graph the particular region, but to get some rough idea. Because right away, if I'm looking at this and if I'm confident in what I've done, I actually know quite a bit of information already, just sort of by getting some rough visualization. And I could even think about this sort of in my head. I don't necessarily even have to draw this out. I think drawing it out makes it a little bit better though, so I'd recommend that. But okay, so we have some rough idea as to what a generic version of this type of region would look like, but let's start digging around a bit. If I want to figure out where these two curves intersect, and they're going to intersect where they're equal, then I should be able to set these two functions equal to one another. So here I would really want to focus on the right-hand side, the more interesting parts, and say, okay, so x squared minus 3x is equal to 2x plus 6. And here I want to move everything over to the left side. I want to set this equal to 0 and work from there. So if I subtract 2x over, so x squared, and then minus 3x minus 2x is minus 5x, I want to subtract 6 over as well, and then set this puppy equal to 0. And with this quadratic formula, of course, if we can factor, we want to factor. It looks like this can factor. Of course, if we can factor, that's probably what we want to do. X and x starting each binomial. Two numbers that multiply to negative 6 but add up to negative 5. You think what I'm thinking? I'm thinking negative 6 and a positive 1. So that means I have values x equals 6 and x equals negative 1. And that's where the two curves are going to intersect. So my picture isn't really drawn perfectly, though maybe I was sort of working with a sixth sense here because it wasn't so bad. Kind of looks not too terribly off. But now the question is, okay, I know where they're going to meet, but which curve is the upper curve and which curve is the lower curve? Because if you remember from the lecture video that you watched, we want to be integrating to find the area, but we want the upper function minus the lower function. So which is the upper function? Well, if we look at the sort of, rough sketch we have here, I think it kind of tells the story. But what we could also do, another way to sort of think about this, is we could pick a test value. So if I went ahead, and let's say I wanted to pick a test value, since I just have these two boundary points, that means that I just have to pick one test value in between. So pick a number between negative 1 and 6. I'm going to pick 0. My test value, x equals 0. If I plug into my two functions, let's say I plug into the x squared minus 3x, that gives me 0 squared minus 3 times 0 gives me 0, versus if I plug into the other function, 2 times 0 plus 6 gives me 0 plus 6 gives me 6. So that would be my upper function. So that means the 2x plus 6 is my upper function. And my picture sort of corroborates that too. If we're thinking about how these would look generically, we can get a generic sense for how the region should look. Then we just have to find out the specifics. But so it looks like that linear function should be the upper function. And in fact, a test value shows that this is true. Okay, so that's good. So now what do we want? Well, now we just want to set up the integral. So we'd say, okay, I want to integrate over my region, which we said was from -1 to 6. And we want to integrate, we want upper function minus lower function. I always like to set up like this so I can drop these pieces in. Let me switch back to my yellow. What is my upper function? We said the upper function was 2x plus 6. So upper, keep it all in parentheses, minus my lower function. So then my lower function then must be the x squared minus 3x. This is my upper minus lower. Now I got the parentheses, but what I want to do next is I want to distribute the subtraction through. So we'd say, all right, we have the integral from -1 to 6. Here I have 2x plus 6. I can just remove those parentheses, but now I want to distribute my minus sign in. We get minus x squared, and then minus a negative is plus 3x, and with respect to x. And then we go ahead and we would combine like terms if we can. So -1 to 6. I'm going to put this in descending order. So negative x squared first. 2x plus 3x gives me plus 5x, and then plus 6 with respect to x. And now all that's left is the integration and the evaluation, right? The calculus part of this. So let's go ahead and integrate. If I integrate minus x squared, that's going to give me minus x cubed over 3. We're using the power rule there for integration. Plus my coefficient 5 comes along. If I integrate x, or that's x to the first, I'm going to get x squared over 2. Remember, we add 1 to the exponent and divide by that same new number. Plus, and if I integrate a constant like 6, it's going to give me 6x. And I don't need the arbitrary constant of integration. I don't need the plus c since I have a bounded integral. Now I just have to evaluate. Keep in mind we need that fundamental theorem of calculus part 2, Judgment Day. We're going to evaluate this. We're going to plug in the upper bound of 6 everywhere we have an x. Then we're going to plug in the lower bound of -1 everywhere we have an x. And we're going to subtract in between. So I get my parentheses. When I plug in a 6, I have negative, and then it's going to be 6 cubed divided by 3 plus 5 times 6 squared divided by 2 plus 6 times 6. And then I'm going to subtract away from this what I get when I plug in -1 for x. So that's negative, and then it's a -1 that I'm cubing over 3. Plus 5 times -1 squared over 2, plus 6 times -1. And now we want to go ahead and evaluate this. Okay, let me just sort of give a little bit of a background and a disclaimer here. However you want to do your arithmetic is your business. I'm not going to judge you, I'm not going to try to make you feel bad about what you're doing. Arithmetic can be sort of a weird thing for everybody. It's very personal. How you do your arithmetic might be different than how I do my arithmetic. I don't have a calculator here with me. No calculator, lots of cats. Cats aren't good at arithmetic. So I'm going to have to do this the way that I feel most comfortable. I'm a big fan of Common Core mathematics. They named it after me. They got rid of the Y because it works. So I'm going to do this kind of funky. And if you're watching me thinking, why is he doing that? What's wrong with him? Is he okay? Who hurt him? Then I want you to just remember that you don't have to do it this way, and just make sure we get the same number. We get the same number, then we're all good, right? But so I would look at this right away and panic internally and say, I don't want to do this arithmetic. However, I notice that I can factor out a 6 squared. So with this first set of parentheses, I would bring out a 6 squared. And what am I left with? I'm left with my minus sign and one of the 6's divided by 3 plus. Here I'm left with my 5 and then divided by 2 because I brought out the 6 squared. And here it's really just a 6 times 6, which is 6 squared. So I'm left with a 1, so plus 1. And then I have minus, and then here this other set of parentheses, I can just start working through it. Negative 1, if I cube it, gives me negative 1. And then I have this minus sign that's going to flip the sign on it, so that's now positive 1 over 3 plus. And here I have 5 times negative 1 squared. If I square a negative 1, it gives me positive 1. So 5 times 1 over 2 is 5 over 2. And then here I have 6 times negative 1 is negative 6. So far, so good. Hopefully you're still with me. Hopefully you're not mad at me yet. But let's keep going. So 6 squared, I'm not going to play any games here. 6 squared is, what is that, 36? Of course. And then negative 6 divided by 3 gives me negative 2 plus 5 halves plus 1. And I got to keep that in parentheses. And then if it's all the same, I'm just going to bring this minus sign through into this other set of parentheses and say minus 1/3 minus 5 halves plus 6. Seems okay to me. I got to keep going. Can't stop, won't stop. Hashtag can't stop, won't stop. 36 in front. Negative 2 plus 1 gives me negative 1 plus 5 halves. Arithmetic, right? I feel like we're doing more arithmetic than calculus. Let me think about getting a common denominator here with the two fractions that I have next, negative 1/3, negative 5 halves. I would want to go to the 1/3 and multiply by 2 over 2. I'd want to go to the 5 halves and multiply by 3 over 3. So that's going to give me minus 2 over 6, minus 15 over 6. And then I have this plus 6. I'm not going to get that into a common denominator yet because I want to see what else is going on here. We'll see, right? With any arithmetic, it's a lot of, you feel like you're out in the middle of the desert, in the middle of nowhere in the dark, just hoping that everything works out okay. If I get a common denominator here, negative 1, let me just scribble over it. That's a 2 over 2, negative 2 over 2. So then 5 halves plus negative 2 over 2 gives me 3 halves. And then I can combine these two together. Negative 2 over 6 minus 15 over 6 gives me negative 17 over 6 plus 6. I hope you haven't clicked off the video yet. That would make me so sad. I'm almost done. Bear with me. I lost my calculator in the shuffle. I don't know where it is. I screamed out its name and it wouldn't return. 36 divided by 2. I got a good feeling I can get some integer here. So 36 divided by 2 is going to give me 18. I still got to multiply by 3. Minus 17/6 plus 6. Almost there. 18 times 3 is going to give me 54. Minus 17 over 6 plus 6. Let me please combine these integers. 54 plus 6 is going to give me 60 minus 17 over 6. Now I'm going to get a common denominator. I'm going to think of 60 like 60 over 1, multiply by 6 over 6. It's going to give me 360 over 6 minus 17 over 6. If I go ahead and subtract, that's going to give me 343 over 6. And hey, didn't need a calculator, didn't even need the cats, to be honest with you. Hopefully that wasn't too painful. If you're not already doing this, put the video on like 2 times speed and just like rip right through it. But if you need to slow it down or rewind, I'm here for that too. Let's take a look at some more examples. Let's find the area bounded between, now we have two curves. We have x as a function of y, x is y squared minus 2y, and x is y minus y squared. And I like to start by finding the bounds on the region. I can do that by setting the curves equal. So y squared minus 2y equals y minus y squared. I like to get everything on one side, of course. If I add y squared over, that gives me 2y squared. If I subtract y, that gives me minus 3y equals 0. And then let's factor. I can factor out a y, and that leaves me with 2y minus 3 in parentheses equals 0. And then I can go ahead and think about the product property of 0, that either one of the factors could be 0, so that means y could be 0, gives me one value, or 2y minus 3 could be 0, and then we know how to solve this, right? Move the 3 over, divide by 2, so y equals 3 halves is the other. So I know where these are going to intersect when y is 0 and when y is 3 halves. And keep in mind, I didn't want to try to solve for y. I wouldn't be able to solve for y, so just work with them as it is, right? That's sort of the idea here. Now, if I want to know which is the upper function or which is the lower function, and sort of upper and lower, we'll talk about this in just a bit, I can get away with that same trick that I did using a test value. I think test values will make maybe a bit more sense here, but let's talk a bit further about it afterwards. Test value, I want to be picking y. I'm treating y as my input in this case, as sort of the independent variable, which is a bit of a role reversal. But I want to pick a value between 0 and 3 halves. I would say 1. Let me pick y equals 1 and see what happens. If I plug into this first curve, and I'm plugging in for y, I get x is 1 squared minus 2 times 1, which is 1 minus 2, which is negative 1. If I plug into this next curve, I get x is 1 minus 1 squared, which is 1 minus 1, which gives me 0. And 0 is larger than negative 1, so that means that came from the y minus y squared. That means that must be the upper function in this case. However, if we were to try to get a visualization of this region, some small kind of graph, we would see something very interesting, and I want to sort of take pause to point that out. If I complete these as ordered pairs, let's say if I plug y in as 0, in both cases I get x is 0, which gives me the ordered pair 0, 0. If I plug in 3 halves for y, I could plug into either, it doesn't matter, because these should both be intersecting there. So it doesn't matter. I think this one maybe looks better, maybe this one looks better. Plug into one of them. When y is 3 halves, I get x is 3 halves squared minus 2 times 3 halves. 3 over 2 times 3 over 2 is 9 over 4. Minus, here the 2's cancel, so that gives me minus 3, but I can get a common denominator, multiply that by 4 over 4. Yeah, 9 over 4 minus 12 over 4 gives me negative 3/4. And this is just so I can have a more reliable visualization here. We're saying when x is negative 3/4, that's what we get when y is 3 halves. So then if I want to try to graph these, try to do my best, x-axis, my y-axis. Let me get some different colors here. Let's do this first curve in pink, the y squared minus 2y. Now right away, we know that these are both going to intersect when x is 0 and y is 0, so right at the origin. And then when x is negative 3/4, so that's a bit leftward, and then y is 3 halves. These are the points of intersection. But for this first curve, I need some third point in order to sort of, graph it to get an idea as to how it looks. And this was the y squared minus 2y. We said when y is 1, that gave me x is negative 1. So that has an ordered pair, negative 1, 1. So negative 1, 1 be sort of here-ish. And then I can get an idea as to how the rest should look. Something like this. And this would be this first curve, y squared minus 2y. We'll do the other one in blue since we've been sort of doing the blue for it anyways. It shares these 2 points, the points of intersection that we found. But then we need a third point, of course. We said for that, when y is 1, we get x is 0. So when y is 1, x is 0, and then we can go ahead and build the curve this way too. Probably does something like that. And we can see this region here that we're looking at in between, and we can really get an idea as to what this concept means, upper function minus lower function, when we're dealing with this sort of change in orientation, because we don't have y as a function of x, we have x as a function of y. And what I want to sort of point out is that when we say the upper function, we really mean the rightmost function. So here we want the rightmost function minus the leftmost function. Gives us sort of a different way to think about upper minus lower, is sort of the idea here. The function that pushes out to the right is going to be the upper function. We sort of think about this switched like this. Okay, well, with that in mind, and we sort of got that information from the test value already, but I don't want to skip over, I think, important information to the problem, we'd say, well, let's go ahead and set this up. So we found our bounds. We did that first. That's from 0 to 3/2. And then we want upper minus lower, which is really rightmost minus leftmost. We said the upper function is y minus y squared. And then the lower function, as it were, is the y squared minus 2y. And in this case, we're going to be integrating with respect to y, since that's the variable that we're working with. Let's bring that subtraction through. So we'd say the integral from 0 to 3/2. We have y minus y squared minus y squared plus 2y. Remember, we're thinking about distributing that minus sign through. We'd say the integral from 0 to 3/2. We have a minus 2y squared, and then a plus 3y with respect to y. And we would want to integrate this. So we'd say -2 comes along as the coefficient. Integrate y squared with respect to y gives us y cubed over 3. Plus 3 comes along as the coefficient. Integrate y with respect to y gives us y squared over 2. And that's from 0 to 3/2. And I want to plug in my upper bound, my lower bound, and subtract in between. Just as a step before doing that, let me bring these coefficients out in front a little bit more than they already are. This is going to be a very small move. I think you're going to see why I like this in just a second. Let me bring this -2/3 right out in front. That's not what I said. -2, let me... That's why we got erasers, right? We have the negative and then 2/3. I wrote the 3. I want the 2/3 times y cubed plus, and then we said 3/2. Get that 2 out with the 3. 3/2 y squared. Seems nitpicky, but I'm going to be plugging in these fractions. I want to be able to see everything a little bit better. I don't want fractions divided by fractions. I'm avoiding complex fractions. This is going to make it a bit easier for me. But same old stuff, right? Plug in the upper bound first. So that's -2/3. And then we're going to have 3/2 cubed plus 3/2 times 3/2 squared. Then I'm going to subtract away from this what I get when I plug in the lower bound for y. And that's -2/3 times 0 cubed plus 3/2 times 0 squared. And I want to point out right away, plugging in that lower bound, you're probably noticing that too. When I plug in 0 for y, it's going to give me 0 for each of these terms. Since y is a factor on everything, plugging in 0 for y gives me a factor of 0 for everything. So this is just going to be a 0. So I'm left with what I have here, really, the upper bound evaluation, -2/3 times 3/2 cubed plus 3/2 times 3/2 squared, and that's just -0. Again, your arithmetic, your business. I would look at this and I would notice something very cool right away, that I can actually factor out a 3/2 cubed. I have it in the first term, and it's actually my second term as well. I have a 3/2 times 3/2 squared. Is that not a 3/2 cubed? Yes, it is. So I'm going to bring out that 3/2 cubed, and I'm left with -2/3 for the first term, plus I factored everything out of the second term, so it's left with +1. And I can go from here now. So I'll say, okay, so this is 3/2 cubed, or that's really 3 cubed over 2 cubed. Can get a common denominator here. Think of 1 like 3/3. Negative 2/3 plus 3/3 gives me positive 1/3. And then I can even reduce across the fraction a bit. 3 cubed divided by 3 gives me 3 squared divided by 2 cubed. We'd say this is 9/8, 9/8. So if you're looking back at that region wondering, hey, what is the area in there? Well, 9/8 units. We got it. We'll take a look at one more sort of problem set question for 6.1, area between curves. We're just going to do the setup only this time. I want to find the area bounded between, now I have 3 curves, y equals square root of x, y is 1/4 x, and x is 25. And I want to get an idea as to how this is going to look. Now, I could go ahead and start with some rough idea as to how my graph is going to look. I can get the information that I need and try to build off of that. So let's go ahead and start. Here's my x and my y axes. And one of my functions right away jumps out at me. Not literally, ha ha ha. But I notice it. X equals 25. That is going to be a vertical line fixed at x equals 25. So I get this vertical line at x equals 25. It's one of my curves here. And then I have the square root function, just the parent function, the elementary function, and then I have a linear function. So I'd say, well, let me go, I'll do the same order, pink and then blue for those. Square root of x, I know how that looks sort of generally. I'm not trying to draw this to any great scale. Here's my square root function. Looks something like this, and then it's going to run into that wall at x equals 25. And I have an idea as to how a linear function should look like 1/4 x, but the question is always, is it going to be above? Is it going to be below? I want to know that maybe before I start drawing it. So a good question would be, what's going on with these two curves? X equals 25, there's not a lot we can say about it. It's a vertical line out 25 units. End of story. But what about these other two curves? Do they intersect? If they do, where do they intersect? Let's figure that out. So I'm going to focus on square root of x and 1/4 x, and I'm going to set them equal. I'm going to try to find if they have a point of intersection. Now, what would I do first? I would maybe multiply the 4 over. 4 square root x equals x. And then in order to work through this, we would want to square both sides. So 4 square root x quantity, I want to square it. X, I want to square that as well. So what is this going to give me? Well, 4 times 4 gives me 16. Radical x times radical x is x equals x squared. And I want to move everything over to one side so I can set this equal to 0. You could probably look at this and figure out what the solutions are by inspection, but you know me, born to be mild. So let me subtract over and say 0 equals x squared minus 16x. I can factor an x out, and I have x minus 16 left over, which gives me two values, x equals 0, x equals 16. So these two functions, the square root function and the linear function, are going to intersect at 0 at the origin, but then also at x equals 16. So where is x equals 16? I don't really know. It's probably somewhere like here, roughly. Does the picture have to look great? No. Are we going to put it up on the fridge later? Probably. Does it have to look perfect? No. So we said it's going to intersect at x equals 0, but also when x is 16, these curves are going to intersect. Okay, that's great information, friend, but I also want to know which is the upper function and which is the lower function. Yes. So what I can do then is I can go ahead and pick a test value in each of these regions. Something between 0 and 16, I'll be honest, I would just pick one. Say test value, x equals 1. We have square root of x is going to give us square root of 1, which is 1. And then we have 1/4 x, which is going to give us 1/4 times 1, which is 1/4. And of course, 1 is greater than 1/4, which means that on the region from 0 to 16, so I picked a test value between 0 and 16 for this, that the square root function is actually above is actually above, which means that this line 1/4 x, maybe you were already thinking this, is underneath, and it's supposed to look like a straight line. Don't give me a hard time. And then they intersect there. But what about afterwards? Well, look, you probably have a good idea or an intuition that after they intersect, they're going to trade behaviors. And that's true. If I wanted to find a way to sort of really know that for certain, just pick another test value. And in fact, I could use a test value of 25. I could say I know they're going to intersect at 16 when x is 16, but if I want to know if it, if this behavior changes or sort of confirm that to corroborate it, I could use the wall at x equals 25 to give me an idea. And sure, x equals 25, we would say square root of 25 gives us 5. And then we would say 25 divided by 4, or 1/4 times 25. And of course, this is going to be larger now. We would say, well, 25 divided by 5 gives me 5. 25 divided by 4 is a larger number than smaller denominator, stuff like that. So we do have that role reversal where the linear function has that linear movement, but then after x equals 16, it now becomes the upper function. This is important to understand because in order to find the area of this region involving these three curves, we actually have two separate regions. We have this region from 0 to 16, where we have upper function as square root and lower function as 1/4 x. Then we also have the region from x equals 16 to x equals 25, where they trade spots. So in order to set this up, we're going to need two separate integrals. So we'd say for our setup, we want to integrate first from 0 to 16. And for that, we said the upper function was square root of x minus the lower function was 1/4 x with respect to x. And then we're going to want the rest of the way, which is going to pick up from 16 to 25. And now the upper function is 1/4 x minus the lower function is square root of x, and with respect to x. And what do I want to do with these two integrals after I compute them? Well, if I want to know, I find the area of this piece and the area of this other piece, and I want to know the full area, I'd add them together, right? So we'd say add them together. And we said just the setup only, so I'm going to leave you here with the setup. If you're looking to integrate something like this, I would give you a little helpful pro tip. I would say remember square root of x is x to the 1/2 power, getting that fractional exponent so we can integrate it using the power rule. So there we have it. We got our setup. Find these separately. It's sort of a 2-for-1. We get two math problems in one math problem, which is great. You're getting your money that way. Find the answers to each of these integrals, add them up, and get that final answer. I have this page for extra notes. You are awesome. Smiley face. Get an exclamation point. Get a couple. Get 3. If you're still with me, thank you. It's great to be here. What can I say? Let's keep talking. Let's go to 6.2. Let's talk about the volumes. Let's talk about the washer and the disk method, which should be next for us in the course. So you should have, again, watched this lecture video already. We're just going to be refreshing a bit of ideas with some extra questions. Again, feel free to work through these on your own. Check back. Make sure we're getting the same answers. But I want to find the volume V of the solid obtained by rotating the region bounded by the given curves about the specified line. And here we have x equals 2 times square root of 3y, x equals 0, y equals 7, and we're rotating about the y-axis. Okay, so we like pictures, right? X-axis, y-axis. Label them. One of the curves is x equals 0. Now, x equals 0 is a vertical line at x equals 0, which is just the y-axis. X equals 0 is a funny way of saying the y-axis, or vice versa. And y equals 7, for example, if this is where 7 is, y equals 7 is a horizontal line. Oh, don't judge my horizontal line. He's doing the best he can. That's a horizontal line fixed up 7 units. Okay. So 2 of these curves are already out of the way. Now I want to know how this x equals 2 times square root of 3y is going to look. If I pick some test values, let me do this in, I got to get some different colors. We like blue. I like the blue. Let me know in the comments below if you like the blue. If I let y be 0, then I'm going to get 2 times square root of 3 times 0, which is 2 times square root of 0, which is 2 times 0, which is 0. So that gives me x is 0, which gives me a point at the origin. And I'm going to need another point, at least. Right? Get as many as makes you comfortable, but I'm going to want at least one more. If I look at this and I think, well, what's going to play nicely here? I think picking y to be 3 is a good move. So I'd say, well, what about when y is 3? If y is 3, then x is 2 times square root of 3 times 3. That's really a 3 squared, right? So this gives me 2 times 3, gives me x is 6. So I have another ordered pair. When y is 3, it just so happens that x is 6, so 6 comma 3. So let's say that if I go out 6 units in the x direction, and then I'm up 3 units in the y direction, I get some point, something like this. And I can go ahead and connect. This is going to look like a root function, but it is kind of oriented a bit differently, and it's got some different stretch factor. But in general, something that looks like this. I just want to get a rough sketch. For anything in 6.2 talking about the washer and disk method, a rough sketch is really all that we need. Once we get the rough sketch, we should be in business. Now I want to talk about rotating this though. So this is my bounded region. I have x equals 0, y equals 7, and then my curve here in blue, x equals 2 radical 3y, and this is the region that I want. But I want to rotate this region about the y-axis. So then here, if I rotate about the y-axis, and here's my y-axis going up and down, it's acting like a mirror. So I want to try to treat it like a mirror. I wish I had a bit more room for this, but make do with what we have. And there's my sort of rotated region. Definitely not drawn perfectly to scale. Let me get a bit of a better depiction of it. I think sometimes when we go through and get these rough sketches, it's not a bad idea to figure out how the region looks first, and then we can try to improve on that sketch. So we had the line, and then we had our curve, and this was our original region, and then we rotated this about the y-axis. So something that looks like this, roughly. Is it perfect? No. Is it modern art? Yeah. Now what we have in this case is an instance of the disk method. So what we would want to do is we want to think about how we could sort of build out the volume of this shape, and we would want to use disks to do this, which would be like washers or rings that are completely filled in. So we call them disks. And I could start sort of lower and get one sort of idea of how a disk would look. And then I could sort of move this up along. Get another example of how a disk would look. And I could go all the way up to sort of the top and get an idea of how the disk would look. And for each of these, I think it's a good idea to think about how the radius is going to look. So that wants to go from our axis of rotation, rotating about the y-axis. And I always want to draw this to the original region, not the rotated region, the original region. Here I can draw in my radii. So this is what we're looking at. And there's going to be infinitely many of these. We're going to stack them in this vertical fashion. They're going to have this negligible thickness. There's going to be infinitely many of them is the idea. But I want you to notice that the way that this is oriented, how we're going to be stacking this, means we're sort of stacking them in the y direction, in the vertical direction. I want you to sort of take notice of that. And with the disk method, we have a very generic formula for the volume, right? We're integrating from A to B, and it's going to be pi times our radius squared. And then in this case, we're saying it's going to be in the y direction, movements in the y direction. So this could be with respect to x. I'll put it dx here, but this example is going to be with respect to y, which can sometimes happen. So be on the lookout. Now, as I'm stacking these, we're going to start at y equals 0, and we're going to go up, 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 until we get to the very top, which is at y equals 7. We said y equals 7 was that curve. So setting this up, we'd say my bounds are going to be from 0 to 7. We have pi times, and then I want the radius squared. And then we're going to integrate with respect to y, since our bounds are bounds on y. In each of these cases, right, the radius is different. We can see that it's going out further and further, but what dictates the radius is this curve here. And that curve was the function x equals 2 times radical 3y. So we'd say, well, this is giving us the radius. It's going out until it reaches that curve, and then it's stopping. So that's 2 radical 3y for my radius, and then I want to square that and multiply by pi and integrate. So we got our setup. Now we can go through the rest of this, the calculus for it. I can bring the pi in front, and then I'm integrating from 0 to 7. 2 times 2, since I got to square it, gives me 4. Radical 3y times radical 3y gives me 3y, and then I'm integrating with respect to y. And then I'd say for this, what I could do is I could go ahead and just bring the coefficient out in front. So I'd say 4 times 3 is 12, so that's a 12 can join the pi. And then I want to integrate y with respect to y. And that's going to give me y squared divided by 2. And this is from 0 to 7. I can divide my coefficient by 2, so 12 divided by 2 gives me 6 pi. And then I still have my y squared from 0 to 7. So then I want to evaluate this. So we'd say 6 pi, and then plugging in my upper and lower bounds in for y, I'm going to leave my coefficient factored in front. So we get 7 squared minus 0 squared. So we have 6 pi times 7 squared is 49, minus 0 squared is 0. So we have 6 pi times 49. And then however you want to multiply this is fine. I would be lazy. I wouldn't want to do this. I'd be like, I don't want to do arithmetic, but what can I do? I can do 50 minus 1 instead is the same as 49. I can just distribute. Is it going to be worth your time? I don't know. It makes it easier for me. So this is going to give me, what is this, 300 pi minus 6 pi. So that looks to me like we got 294 pi. That's a lot of pi. And we did it. And that's going to give us the volume. Now, when constructing these shapes, I like to think a little bit about what they could be used for. This is going to be sort of completely solid since we use the disk method. So it kind of looks like a popcorn bowl to me, but there's no space inside of it. So you just kind of got to like set the popcorn on top of it and then like kind of flick it off or try to pick it and then eat it. It seems very kind of useless just for show, or like a gag gift that you would give to someone who you don't like. But it's fun to think about, you know, not only finding the volume of these things, but what such a solid could be used for in a practical application. Let's take a look at another example. Find the volume V of the solid obtained by rotating the region bounded by, here we have curves y equals 5x to the 6th, y equals 5x. We have a restriction that x is greater than or equal to 0, and it's about the x-axis is how we're rotating. You know me, I like to get sort of a graph going. Maybe before even doing that, I might want to find out where these two functions intersect. So I'd say, what about the intersection? 5x to the 6th and 5x, set them equal. I can divide both sides by 5 right away, so x to the 6th equals x. I can subtract x over, so x to the 6th minus x equals 0. And I can factor x out. That leaves me with x to the 5th minus 1 equals 0. So two possibilities here, you better believe it, that x could be 0, gives me a solution, or x to the 5th minus 1 could be 0, means x to the 5th is equal to 1. So then x would have to be positive 1. Notice a negative 1 wouldn't work here. Wouldn't work. The sign would be off. So I have two values that we're going to intersect it. X equals 0 and x equals 1, which is good to know. So I can get a picture. So x equals 0, and then I'll sort of exaggerate the scale a bit at x equals 1. We're going to have some more stuff going on. And let me go ahead and start with the linear function, 5x, because I know how y equals 5x is going to look. When x is 0, it's going to give me 0. When x is 1, it's going to give me 5. And my scale is going to be not really drawn to scale perfectly, but let's say y equals 5 is up here, and then I get this line connecting. So this is the function y equals 5x. Now I also want to draw y equals 5x to the 6th. I know it's going to intersect at those 2 points. We'll do this one in the neon pink. I know it's going to intersect at 0 and when x is 1. But I want to know, what about in between? Is it above? Is it beneath? It's going to have some sort of curvature to it, but I want to know, how does that look? So I could pick a test value. Between 0 and 1, I could pick, for example, 1/2. And think about 5 times 1/2 to the power of 6, which this is really 5 divided by 2 to the 6th, versus 5 times 1/2, which is 5 over 2. Now, which of these is larger? Well, 5/2 is going to be larger, right? If I take 5 and divide it by 2, it's going to be bigger than if I take 5 and divide it by 2 to the 6th. So we'd say here, bigger denominator, smaller fraction. So this is actually going to be underneath. And since it's, got that exponent 5x to the 6th, it's going to have some curvature to it. It's not linear, of course. So we get this kind of bow to it. I don't probably even need to know that much information to get an idea as to how this looks roughly. It's always good to be thinking about functions and trying to get somewhat accurate representations. And if you want to get more points, get more points. But here we have an idea as to how this region looks, right? Here I have y equals 5x in blue, y equals 5x to the 6th in the pink. We're talking about x being greater than or equal to 0. So we're at the origin and in quadrant 1, it looks like. Now I'm ready to rotate. And I want to rotate this. We'll do the rotated region in red. I want to rotate this about the x-axis. So shame on me, I did not label my axes, but there's my x-axis. And that's going to act as a mirror. We're looking into the mirror, and we're going to try to reflect this. So the reflected region in red, there's my sort of linear function. And then I want this bowed curve, I want to reflect it as best as I can, get a rough idea as to how it looks. There's my reflected region. I'm just going to move myself. Whoa, where am I going? I'm over here now. Who did that to me? Did you do that? I did that. And here we have original region, rotated region. Now I want to get an idea, in this case, how we're going to be working with washers, how a typical washer would look. Let's say here I can draw on a washer. There's my sort of outer ring, and then I have an inner ring as well. And I can move this out. Notice in this case I'm moving out from left to right. I can draw on another washer. There's my outer ring, and then I have this inner ring. We have sort of this rough idea as to how this is going to look. Let me try to clean this up a bit, something like this. And I would do this sort of along the way with these. It's like a dance move, building these washers out. And this, so we said, is going to have to be the washer method, which, just kind of kicks things up a notch from the disk method. We'd say here we're integrating from a to b, and I want pi, and then I want outer radius squared minus inner radius squared with respect to x or with respect to y, right? Depends on the situation. So you say, well, looking at this, we can go ahead and figure out what's going on. We already had our bounds a long time ago from 0 to 1. integrating from 0 to 1. We have pi factored in front, and then I want the outer radius squared minus the inner radius squared. My bounds are on x, so this should be an integral with respect to x, of course. And let's think about what the outer and the inner radius is. So I'm starting here at the axis of rotation. I can put a little point. Let's say if I go out to the outer ring, that's my outer radius. So I can do that here for this first one that I drew, and then I have another one here. Going out to the outer radius, in both cases, I'm going out until I hit this linear function in blue, which is y equals 5x. So for any of these washers, the outer radius is going to be dictated by 5x. Well, okay, what about the inner radius? Well, I'm glad you asked. Let's switch over to the purple. If I go from the center, and this is just this little inner ring, I'm going to go up, but only a little bit until I hit this pink curve. And same over here. I can start the inner ring. I can start here at the axis, and then I'm going to go up for the inner ring until I hit this pink curve. So then the inner radius is going up until I hit that function 5x to the 6th. So inner radius is 5x to the 6th. So outer radius squared minus inner radius squared, side order of pi. Once I have this set up, it really just becomes calculus from there. I want to expand this out though, so we'd say the integral from 0 to 1, pi in front. 5x, if I square it, 5x times 5x is 25x squared, minus 5x to the 6 times 5x to the 6 is 25x to the 12th. Here we're re-raising, so we multiply those exponents, dx. I would factor out the common 25 and say 25 pi, and then I would integrate the power terms. If I integrate x squared, gives me x cubed over 3, minus, if I integrate x to the 12th, I get x to the 13 over 13, and that is from 0 to 1. Just using the power rule there to integrate. And then I can go ahead and work through the evaluation. So 25 pi is going to stay out in front. If I plug in 1 for x, I get 1 cubed over 3 minus 1 to the 13th over 13, minus, when I plug in 0 for x, I get 0 cubed over 3 minus 0 to the 13th over 13. And then I can work through the evaluation. I don't like being over on that side. I like being right here. Hey, it's me again. Let's evaluate. Let's finish this one up. So I have 25 pi factored all the way out in front of all the fun stuff. 1 cubed is 1 divided by 3, minus 1 to the power of 13 is 1, and then we're dividing that by 13. And then minus, here 0 cubed is 0, gives me 0. 0 to the 13th is 0, dividing by some other number that's non-zero gives me 0, so that's all 0. All 0 there. So what am I left with? I'm left with 25 pi times 1/3 minus 1 over 13. Get a common denominator. I can multiply the 1/3 by 13 over 13. I can multiply the 1 over 13 by 3 over 3. So I get 25 pi, 13 over 39 minus 3 over 39. And now these are like fractions, so I can subtract. So 25 pi still in front. 13 minus 3 gives me 10 over 39. And now I can just multiply this out. So we'd say 25 times 10 gives us 250 pi divided by 39. So we found the volume of that solid. And here, it kind of is a bit more. Let's talk about this one. It's 250 pi over 39. So again, I said I think it's fun to think about what these could maybe be used for. This looks like if we were sort of rotating it about and thinking about actually constructing this solid that we have here, it looks like a very ornate sort of like a candy dish maybe, or you could put like some flowers in it if you do that. But since it's like on its side, it's kind of rendering it useless. Like you'd put candy in it and then just kind of fall out and say, well, shouldn't you turn it the other way, like right side up? It's like, well, no, this is how it is. It's always been this way. That's how my candy dishes are. Kind of a cool solid to think about. We're going to take a look at one more example, and this is just the setup only, and that's going to be it for this session. So I want to find the volume by rotating the region bounded by, here I have curves, y equals 7 sine of x, y equals 7 cosine of x, and this is bounded from 0 to pi over 4 in the x direction. We're rotating about y equals -1. Now I can start by finding where these two functions intersect. So we'd say 7 sine of x equals 7 cosine x. Right away I can divide both sides by 7, so this is sine of x equals cosine of x. You can work with tangent. You can think about inverse tangent, arctangent. However, I think this is something we should be able to solve right away by inspection. And since we're restricted to values of x that are between 0 and pi over 4, there's really no ambiguity, right? There's only going to be one value that works. When our sine and cosine equal, well, that's going to be at our 45 degrees, or we want this in radians, that's when x is equal to pi over 4. So that should be comfortable from trigonometry. If you want to talk a bit more about trig stuff, let me know on the discussion board. I want to talk about trig if you want to talk about trig. We can talk about this a bit more in depth there. But hopefully this is familiar. This is where they both take on that cool value, radical 2 divided by 2, and that happens when x is pi over 4 or at 45 degrees. 45 degrees, which is in fact one of my bounding values. So that's kind of interesting to sort of keep in mind. But let's see if we can start using this information to generate some rough sketch. So let's say pi over 4 is out here, 0 is of course here. I got the x-axis, the y-axis. And now I want to graph 7 sine x and 7 cosine x. Let me start with 7 sine x. Now the sine function in general starts at 0 and then creeps up to the height of its amplitude, and it would reach that at like pi over 2. So it's not quite going to get there, but it's going to start that process. So we'd say here 7 sine x, the only real distinction is that its amplitude would be 7, but again it's not going to fully reach it anyways because we're cutting it short at pi over 4. It would still start at 0. It would look like the sine function. It's got this nice kind of curve to it, and then we're kind of clipping it there, but it would keep going up. Well, what about 7 cosine of x? Well, 7 cosine of x is going to start up at 7. Let's say 7 is maybe up here, something like that. And this is now, so it starts at the height of its amplitude with cosine, but it's going to fall down, and it would reach 0 at pi over 2, which again, we're not letting it go all that way, just to pi over 4. So it's going to fall, and then they intersect at pi over 4. This was cosine x, 7 cosine x was the purple. We said 7 sine x was the baby blue. Let me get my axis. There we go. So this is the region that we have, right, from 0 to pi over 4 in the x direction, 7 sine of x in blue, 7 cosine of x in purple. So we get this wedge-like region. And how are we rotating this? Well, we're rotating it about the line y equals -1. This is interesting. This is not one of our principal axes. Y equals -1 is this horizontal line fixed at -1 for y. So then if I wanted to reflect this region, I would use this, I drew this sort of dotted line there to help me out, I would use this as a mirror. And keep in mind, if you're looking at yourself in the mirror and you got your nose right against the mirror, then while your reflection's gonna, your nose that's reflected is gonna touch your nose at the mirror. But if you're like a normal, well, I don't care what you do when you look in the mirror, I'm gonna be honest, that's none of my business. But if you're not sticking your nose against the mirror and the mirror's like here, then there's gonna be some space between you and the mirror. And that's what's happening here. I have this little 1 unit of space for my original region, between that original region and the mirror. So on the other side of the mirror, I want to mimic that 1 unit of space. And then from there, I want to try to get an idea as to how this reflected region is going to look. So I do my best. I'm on my best behavior. kind of, sort of, close enough. Did it not go? It didn't really go out far enough. Let me clean it up a bit. I can do a bit better. Do you believe in me? Let me know in the comments below. These are just rough sketches anyways. Let's see if we can improve on it a little bit in real time. Yeah, looks good. Looks good to me. Sure. So there we have original region, rotated region. And this is going to be another example of our washer method. So how is this going to look? Well, if I draw in a typical washer, there's my outer ring, and then my inner ring, and I can draw more of these, of course. You know, the idea is that there's going to be infinitely many of them. I want you to get an idea as to how we're going to be stacking these, though. It's going to be moving from sort of left to right. So we're moving in the x direction. So this should be with respect to x. And I want to know, of course I do, I want to know what the outer radius and the inner radius are. Outer radius and inner radius. Now this is going to be tough because we're going from the center of our sort of rings for our washer, and the center should be right at the axis of rotation, which is this line y equals -1. If I go out to the outer ring, well, it stops when I reach the cosine function, 7 cosine of x, but I want you to notice that something else has happened. It isn't just going from the x-axis up until it hits that function. It has to travel this extra distance. I have this extra distance of 1 unit because I had moved my mirror to y equals -1. So it has to travel a bit further. So it isn't just 7 cosine of x. I have to travel 1 extra unit. So my outer radius is 7 cosine of x plus 1, because I have this extra 1 unit of distance that I have to travel. Now similarly, we do this in the red so we can see it. If I travel from the center again, and now if I just go up until I hit the inner ring, well, that's dictated by the sine curve, right? 7 sine of x. But it's not the same as traveling from the x-axis to the sine curve. I have this 1 extra unit of travel that I had to do because my axis of rotation was pushed down a bit. So the inner radius, in a similar sense, is going to be 7 sine of x plus 1. 7 sine of x plus 1. So we'd say, okay, well, if that makes sense, then we're ready for our setup. Let's take a look at how this is going to look. We already have the bounds given on x. Or they're actually given with the problem. That's from 0 to pi over 4. So let's say I want to integrate from 0 to pi over 4. I'm going to want pi times, I'm going to want the outer radius squared minus the inner radius squared. We said this is going to be integration with respect to x. Since we have bounds on x, we found these. We said the outer radius is 7 cosine x plus 1. And all of that needs to be treated as the outer radius. And I got to square all of it. And then we said that the inner radius was 7 sine of x plus 1. We had that extra distance we had to travel for each of these. This is our setup, so I'm going to leave you here. Let me just talk a bit of strategy. You do want to FOIL each of these. FOIL, F-O-I-L, multiply it out. And distribute that minus sign through as well. When you get to when you want to integrate, you're going to be dealing probably with a cosine squared and a sine squared. I would want to use some trig identities to help with this. I'm going to tell you what trig identities I like the most, but we can talk a bit about that. I would be working probably with the identity cosine squared is 1/2 quantity 1 plus cosine 2x. And the identity sine squared is 1/2 quantity 1 minus cosine 2x. However, depending on how you view this, you could even use another identity. You're going to wind up with some cosine squared minus sine squared term, and there's an identity for that too, which might actually be useful. But otherwise, if you just have, more bare bones, I think these are good identities to use. But other identities to consider, you can go crazy with it. And then the evaluation. Hey, this is it. Thank you so much for taking a look at our problem set. Wherever you are, I hope you're doing great. No matter what, though, I want you to remember to always keep learning, keep dreaming, and follow your heart. I'm going to see you next time. We're going to do more math together. All right, I'll see you later. Take care.